Hi everyone, I'm Sophie. In this talk, I'm going to talk about random graph matching at Otter threshold Yihong chandeliers. This is a joint work with my co-author Cheng from Georgia Tech, Yihong from Yale, and my advisor Jiaming from Duke. First, let me show you some motivating examples on graph matching. The first one is network de-anonymization. Here, as you can see, we have two networks. One of the network is anonymized. Suppose the two networks correspond to the same group of people. Then by applying the graph matching technique, we can identify the same users across the two networks. The idea behind the scene is that if we're friends on one network, it is also very likely that we're friends on another network. Then utilize the structure of the two networks can help us achieve de-anonymization. The second example is biology. So each network represents a protein-to-protein interaction network. So the node represents the protein. The edge represents their existence and interaction between the two proteins. The first network corresponds to the protein network in human body. The second network corresponds to the protein network in mouse. Then by applying the graph matching technique, we can identify proteins with similar functions across the two species. The third example is on computer vision. Here we have two 3D shapes of the same human body. Then by applying the graph matching technique, we can analyze how human body moves. In the real-world setting, we know that the graph matching problem can be extremely challenging because the network can be on very large scale. For example, Facebook, it contains 2 billion of users and trillion of edges. The network size is extremely large. On the computational perspective, suppose each network only contains 100 nodes. The total number of possible node mappings between the two networks is 100 factorial, which is already super large, not to mention when the network size gets even larger. On the statistical perspective, the two graphs may be correlated, but they're not exactly the same, making this problem even challenging. To formally study this problem, now let me introduce you this popular model called correlated Erdős graph model. Here is a tool example. We have A and B, two networks. Each one of them is an Erdős random graph with n nodes. In this example, n equals to 5. Each two nodes are connected with probability Q. And we say that A and B are edgewise correlated with each other under a hidden node correspondence pi indicated by these dotted lines that map the nodes from A to B. For example, you can view that A and B denotes the same group of people from Nintendo World. A is their friend networks on Facebook. The B is their friend network on Twitter. And here we say that they're edgewise correlated in the following sense. For example, whether Mario and Luigi are friends on Facebook is correlated with whether they're friends on Twitter, and the correlation is captured by parameter rho. In this example here, rho is 0.8. So that's why if you take a closer look, these two networks do not look exactly the same. For example, Princess Peach and Luigi, they're not friends on the first network, but they're friends on the second network. As this correlation parameter rho gets larger and close to 1, the two networks will be more correlated with each other, and they should look more similar. When rho equals to 1, they should look exactly the same. Another key parameter is this n times q. This is the average degree for A and B. You can think it's a measure of graph density. So the larger NQ, the graph will become denser and contains more edges. Then the question becomes that if we only observe the structure of A and B, we want to recover the hidden node correspondence pi between the two networks. In other words, if we don't observe the user identities, can we still identify the same user across the two networks just based on structure of A and B? And here we'll look into the case when the network size diverge. Now let me introduce you the state of the art. Here we focus on polynomial time algorithms. In this table, we have two dimensions. One dimension corresponding to the correlation parameter rho. We divide it into three regimes: extremely high, high, and low correlation regimes. The other dimension is n times q, and we divide it into sparse and dense graphs regimes. The study for the graph matching problem with respect to the correlated Earth-scaling graph model can be traced back to last century. A lot of famous researchers like Barby, Erdős, Bolivas have studied this problem, and they focused on the region when the correlation equals to 1. You can think this is a case when the two networks are isomorphic to each other. In the past decade, a lot of new algorithm has been developed, and these algorithms can tolerate some noises between the two networks. So these algorithms works when the correlation is converging to 1 when the graph size diverge. In the past 2 years, some new algorithm has been developed. These algorithms can work when the correlation is some constant that is smaller than 1. However, they have two limitations. First is that these algorithms only work for the sparse graphs. Second is that these algorithms only work when the correlation is some constant that is really close to 1 and is unspecified. In our work, we actually show that our algorithm could work as long as this correlation is larger than the square root of this Otter's tree counting constant. So this constant comes from the following fact. If you want to count the number of unlabeled trees with capital N number of edges, as this capital N diverge, then the size of this family of unlabeled trees actually grows exponential with respect to the tree size. And the growth rate is this 1 over alpha. Now let me talk about our main results. What we show is that if the correlation is larger than the square root of the tree counting constant, then as the graph size diverge, our algorithm scales with the network size and it succeeds with high probability, such that if the average degree of A and B is larger than some constant C, then our algorithm could achieve partial recovery. That means we can correctly identify a positive constant fraction of users between the two networks. If the graph gets even denser, here just means that average degree of A and B diverge as the graph size diverge, then our algorithm could achieve almost exact recovery. That means we can correctly identify almost all users between the two networks. If the graph gets even denser and the following conditions satisfied, then we can achieve exact recovery. That means we can correctly identify every user between the two networks. One thing to emphasize is that our algorithm do not make any mismatching error. In other words, I'll never say your account corresponds to another person's account across two networks. Now let me briefly talk about this highlighted condition here. So if you look into the intersection graph between A and B under the hidden node corresponds pi, you can think this intersection graph is also a network that contains all the users, and each two users are connected if they are friends on both A and B. Then this intersection graph itself is also an Earth-scaling random graph with n nodes, and this is its edge probability. Then this condition corresponds to the connectivity threshold of the intersection graph. In other words, if you go below the threshold of log n, then the intersection graph will contain many isolated users. So there is no way that we can distinguish those isolated users from each other. So that's why this condition, highlighted condition, is information theoretically necessary for exact recovery. By the way, in our analysis, we assume the edge probability Q is smaller or equal than 1/2. This is because if the edge probability go beyond 1/2, you can always flip the edges such that the previous edge becomes non-edge, the previous non-edge becomes edges, so that the dense graph can become sparse graph and the result remains the same. Now let me show you a phase transition diagram. Here we focus on exact recovery, where we want to correctly identify all the users between the two networks. We focus on the region when the average degree n times q equals to some constant time log n. So this diagram has two dimensions. One dimension corresponds to the correlation parameter rho, the other corresponding to this constant lambda. In one of our previous work, we showed that this curve is the information theoretical limit, such that if you go below this curve, there's no algorithm could achieve exact recovery regardless of computational efficiency. So we call this gray area as impossible region. If you go above the thresholds here, then that means there exists an algorithm could achieve exact recovery. In this work, what we show is that if the correlation is larger than the square root of this Otter tree counting constant, then we can achieve exact recovery in polynomial time. As you can see, this green region and this gray region, they touches on the threshold here. This implies that our algorithm is in fact information theoretically optimal when the lambda falls into this region here. In fact, it is conjectured that this red region is hard in the sense that if you go below the threshold, then there is no polynomial time algorithm could achieve exact recovery. We have some evidence that in our previous work, we showed that all the low-degree polynomial estimator fails when the correlation is converging to 0. And there is a subsequent work by Ganasali, Masoli, Sermanjan's work. They show that their local algorithm fails when the correlation is below the threshold here in the sparse region. By the way, their work also can achieve this threshold when rho goes to square root alpha. The only difference is that their algorithm could only work for the sparse graph, and their algorithm could only achieve partial recovery, and they could also have some mismatching errors. Now let me talk about the algorithm. Let's look into the toy example where each network only have 5 nodes. For simplicity, let's just label the nodes using 1, 2, 3, 4, 5. The goal is we want to develop an efficient algorithm that can map the nodes from A to B so that we can identify the same user across the 2 networks. Here is a meta algorithm. The first step is called signature embedding. So based on the structure of A, we construct a vertex signature for each vertex in A. You can think we're doing some feature engineering so that we can capture the feature for each vertex, and we denote the signature using S1 to S5. We can follow the same rule to construct the signature for each vertex in B and denote it using T1 to T5. Having the signature for each vertex in A and B, we can then compute the similarity score. Fix the vertex I in A and vertex J in B. The similarity scores between I and J is computed based on the signatures of Si and Tj. And we want that if the 2 vertices, they correspond to the same user, then we want the signatures to be close to each other, so the score is relatively large. If the 2 vertices are not corresponding to the same user, we want the 2 signatures to be far apart, so the score is relatively small. And the question becomes how to construct the vertex signature. One simple example is just using the degree, like how many neighbors each vertex have. But you can also view it as using the popularity for each user. The idea is that if one person is popular in one network, it's also very likely this person is popular in another network. But the issue is it can be multiple persons are all popular in one network, and there's no way that we can distinguish them using the degree or popularity information. How about we use more information, like the degree of neighbors? This actually works, but this only works when the correlation is converging to 1. Otherwise, this algorithm does not work. The reason behind this is that if the 2 networks, the correlation is not converging to 1, then one person's friends group in one network can be very different from his or her friend group another network. Then using the friend's popularity cannot help us to distinguish who this person is. How about we use more information, not just one hop neighborhood, but M hop neighborhood. This leads to the third example, the local tree structure. The good thing here is we're using more information like M-hop neighborhood information, but the issue is that here, it requires a local neighborhood to be a tree structure, so the graph has to be sparse. As you can see that all these examples here are either sensitive to noise or only work in a sparse region. We need something completely different, and this leads to our idea via using the subgraph count. Now let me introduce you subgraph count by looking to this simple example here. Let's fix a subgraph H that is a wedge that has 2 edges. To count how many copies of H in A, we can get that there are 6 copies of that. This is one way that we can capture some graph information. In other words, this is more like a global information about the structure of A. The subgraph count itself is very popular in both theory and practice, which is related to the motive counting. However, as I mentioned in the beginning of the algorithm part, what we want is to capture the vertex information, to construct a vertex feature instead of the global information. Then the question leads to how to use subgraph count to capture the information of vertex I so that I can distinguish it from all other vertices. It leads to the rooted subgraph count. Let's fix a vertex in H, denoted by the solid node, and we call it as a root. Then here we're going to count how many copies of H rooted at vertex I appear in graph A and denote it as WIHA. So I is the vertex we try to capture the information, H is a rooted subgraph, and A is a network we conduct our analysis on. In this example here, there are only 3 copies of H rooted at vertex I appears in A. And this quantity equals to 3. As you can see, this is one way that we can capture some vertex information. And the idea behind this is that we want to construct a rich family of rooted subgraphs so that each root subgraph, by counting it, can help us capture some information about the vertex. Then we can combine the information over this rich family of rooted subgraph so that we can make the vertex signature to be more informative. Having this idea of construct a rich family of rooted subgraph, then now let me introduce a roadmap of how we conduct graph matching. The first step is we construct a family of rooted subgraph. Each rooted subgraph has capital N number of edges. In this short example here, capital N equals to 4. So each rooted subgraph has 4 edges, and the solid node represents its root. The first step is to construct the vertex signature. So for each vertex I in A, its signature is a vector, such that each entry corresponding to a rooted subgraph count with respect to one rooted subgraph in this family here. The issue with this way is that we can figure out all the entries can be highly correlated with each other's across different rooted subgraph, which is not a good thing, because the reason we construct this rich family is we want different rooted subgraph to capture different information about the vertex. So to resolve this high correlation issue, what we do is conduct another so-called rooted sign subgraph count. So let's first center the adjacency matrix of A so that we can view A as a complete graph so that each 2 vertices are connected. And the edge will have a corresponding weight, and the weight depends on the center adjacency matrix. And then having this weighted complete graph of A, then we're going to count the number of weighted copies of H appears in this complete graph, and we call it as a rooted sign subgraph count. And having this, we can show that all the entries becomes uncorrelated with each other and resolve the previous issue. We can do the same thing for each vertex in B, and then we construct its corresponding vertex signature and show that by doing this rooted sign subgraph count, all the entries becomes uncorrelated. And then we can compute the similarity score by taking the inner product with respect to these 2 signatures. And here the alt H denotes the number of automorphism of H. You can think this is number of symmetries of a rooted subgraph. Having the similar scores for each pair of vertices I in A and J in B, then we're going to match these 2 vertices if the score is above certain threshold. And here we have the following observation. For the fixed rooted subgraph H, then the corresponding counting of this H rooted at vertex I in A versus the counting of H rooted at vertex J in B, these 2 quantities are correlated if and only if I and J, they are the true pair. In other words, they are the same users across the 2 networks. Otherwise, these 2 quantities will be uncorrelated. Having this property, then we can compute the expectations of the score under the case when I and J, they are true pair, and the case they're fake pair. Because we know these 2 terms are uncorrelated if I and J are fake pair, then we know the expectation of the score is always equal to 0. And when I and J they're true pair, then the expectation of the score will be some quantity far away from 0, and we denote the expectation as mu. So this is called the mean separations under these 2 cases. However, this is not enough. We also want the fluctuation of the score to be relatively small compared to the mean separation. For example, this is the ideal case, where we have the score is highly concentrated around 0 when I and j they're fake pair, and concentrated around mu when I and j are true pair. And then having this ideal case, then we can pick the threshold tau to be, say, 1 over mu. Then we're going to match all the vertices if their score is above the threshold, and don't match them if the score is below the threshold. Then we can guarantee that all the outputs are going to be the true pairs. Then the question leads to which family of rooted subgraph to choose so that we can guarantee the fluctuation of the score is relatively small compared to the mean separation. To control the fluctuation of the score, it's sufficient to look into the second moment of the score, and then we need to explain the summation when we compute the second moment. If we ignore the cross correlations between different terms within the summation here, then we can compute this ratio here, which is a variance divided by mu squared. You can think this is a matter of the fluctuation with respect to the mean separation. And this ratio is roughly 1 divided by the size of the family times the quantity depends on both the correlation and the size for each rooted subgraph in the family. And we want this ratio to converge to 0 so that we can have the fluctuation to be relatively small compared to the mean separation. Then this requires two things. One is we need this family to be rich so that the cardinality of the family grows at least exponential with respect to the size of each rooted subgraph. The second thing is we also need each rooted subgraph H to be large enough so that capital N grows with respect to the size of A and B. Lastly, we also need this H to be simple so that we can count it efficiently. And this rich, large, simple criteria leads to the choice of picking this family to be a family of trees. And we know that if we pick it to be a family of trees, then this family grows exponential with respect to the tree size, and the growth rate is 1 over this Otter's tree counting constant. Then we can plug in this cardinality of the family to the above ratio. And we can show that this ratio converges to 0 if the correlation is larger than the square root of this Otter's tree counting constant. And if H is a tree, it is simple to be counted via a randomized algorithm called color coding. However, note that we cannot ignore the cross correlation between different terms within the summation here. So all of these calculations shown here are ignoring the existence of the cross correlations, which is not okay. So that's why we need to construct a special family of trees. And we want this special family of trees to suppress this undesirable cross correlation between different terms within the summation so that we can control the fluctuation of the score. And we also want this special family of trees has to be rich enough. And that's why we construct a special family of trees called chandeliers. And the reason we call it as chandeliers is because it looks like a chandelier is on the ceiling. And the solid node is a root. The white parts are called wires. Each wire is the path. And the blue part are the bulbs. Each bulb is a rooted subtree. And this chandelier will have L branches. One interesting fact about the chandelier is that as long as we can ensure that the bulbs contain more edges than the wires, then we can always have a lot of freedoms at the bottom part of the trees. In other words, even though we restrict the chandeliers to have this special structure, the cardinality of these families is almost the same as the cardinality of the family of all trees. So the family is still rich enough. And having these chandeliers, we can further show that the variance divided by mu squared for fake pairs is on the order of little o1 divided by n squared. As long as the correlation is larger than the square root of the Otter's tree counting constant, and the chandeliers is logarithmic with respect to the graph size of A and B. For the true pair, this ratio will be little o1. That's why we can pick a threshold, say it's mu over 2, and we're going to match all the vertices I with j if their scores is above this threshold, and don't match them otherwise. As you can see here, we're only going to match the true pairs, but there will be a vanishing fraction of vertex pairs, even though they're true pair, but our algorithm do not output this part. So that's why directly applying the above techniques, we can only achieve almost exact recovery with no mismatching error. And when the degree is large and this condition is satisfied, then we can further boost the almost exact recovery to exact recovery. And the technique we used here is like, because we already correctly match almost all vertices between the two graphs, then we can use all these correct match vertices as seed to gradually match the remaining vertices. Now let me briefly talk about why chandeliers work. The key is we want to control this variance of the score. So we need to explain the summations and have this following term. So this requires us to analyze and enumerate all possible overlapping patterns of 4 rooted trees. And what we figure out is that when the union graph that contains a cycle, then this case will contribute less to the variance. The case when the union graphs are trees, this will become the dominating term in variance of the score. And here let's look into a toy example, and let's just look into the overlapping pattern with respect to only 2 chandeliers. And here are 2 cases. One is when the union graph actually contains a cycle. As you can see here, the 2 branches of the 2 chandelier overlap and then separate out. However, they're both touch with each other, so that's why there is a cycle here. But then the other case we've seen here is that if the branches touches, but is separate out, and the bulb does not touch with each other. So this is a case when the union graph is a tree. This is just a toy illustration showing you that we need to control the case when the union graph are trees. And because of the special structure of the chandeliers, we know that once they overlap with each other and the branch touch with each other, once the branch spread out, the bulb cannot touch with each other, so that the overall union graph are trees. And having the special structure of trees, chandeliers, we can have our analysis go through. Now, let me make a quick conclusion. We developed the first polynomial time algorithm that achieved exact and almost exact recovery with an explicit constant correlation for both sparse and dense graphs via counting a special family of trees we constructed called chandeliers. And here is a reference.